Yes.
Okay, great. Thanks, Tom. And thank you, everyone, for sticking around today. I know it's tough. I think I speak on behalf of Travis and John both, so we appreciate you, everybody, sticking around for this last session. So today I'm going to talk a bit about some of the work that the Nature Conservancy has been doing in the headwater region of the McConnell River watershed, specifically working at constructed wetlands and the role that they can play in reducing nitrogen and phosphorus levels from tile drainage waters. And so before I get too far along, I do want to acknowledge my co-authors, first Maria Lemke, also with the Nature Conservancy, Dave Kovacic and Mike Wallace from the University of Illinois, and then also Jacob Berkowitz and Catherine Van Zomeren from the U.S. Corps of Engineers out of Mississippi. So even though Nature Conservancy tends to focus on natural sites, we actually have been working in agriculture for quite some time now. Specifically, the Illinois chapter has been working in the Mackinac headwaters since the late 90s. And part of the reason for this is that it's by far the most dominant landscape in Illinois, which is no surprise to those of us that live here. About 28 million acres of land in Illinois is in some form of production, and that is about 80% of our total land area. And it's also a huge part of our economy as well. It generates about $9 billion annually, and most of that is tied up into corn and soybeans, and then the rest into livestock. So it's a big part of the economy and also a big part of the culture. However, with that big transition of our native landscape to this type of conventional row crop agriculture, we've seen a lot of changes with a lot of different things, but specifically with the way that water moves on our landscape. So we've seen our channelization of ditches to get water off quickly. And then probably what's been a bigger influence is this impact of tile drainage, which is the photo on the right. And if you're unfamiliar with tile drainage, what this is basically a very sophisticated system network of these perforated pipes that are laid anywhere 2 to 4 feet below the soil surface. And those pipes themselves will be anywhere between 4 to 6 inches. Now, tile drainage is not new. This has been around actually since the late 1800s, which was very crude with just digging some shallow ditches and putting in actual clay pipes. But now, as you can see, it's a very sophisticated system, and tiles come in these big coils that can be put into the landscape very efficiently and very quickly. And this is all done just to make sure that these wet soils can be amenable for farming, particularly the type of farming that we have today. But it's to the point now where Illinois has over 12 million acres in some form of tile drainage. And when you couple that with added nutrients, specifically nitrogen and phosphorus, we have a lot of water leaving our watersheds and at a faster rate than ever with added nutrients. So, and it's come to the point now where Illinois contributes about 20% of the nitrogen, 11% of the phosphorus loadings, but only 7% of the total flow to the Gulf of Mexico. So we often battle with Iowa having that title of who's contributing the most to the Gulf of Mexico. So we certainly have a lot of work to do. But the good news is that the Nature Conservancy and many partners have been dealing with this issue and trying to figure out what not only works within the landscape to be the most effective, but also working with farmers and producers to figure out what works best for their farming system. And so what I have here is a map of the Mackinac River watershed. It's located about the middle of the state, and it runs east to west into the Illinois River near Pekin. It's about 730,000 acres in total. And as you can see from this map, anything that's yellow or brown is either corn or soybean. So this is very much a highly agricultural watershed. So we have 3 different research projects going on in the Mackinac. First, our oldest, our Paired Watershed Project, which is down in the lower right corner. That's looking at conservation practices at a small watershed scale. And we've taken some of those lessons learned into our Bloomington Drinking Watersheds project, which is outlined in green there. And those are the watersheds that incorporate Lake Bloomington and Evergreen Lake. But for today's talk, I really just want to focus on the Franklin Research and Demonstration Farm, which is looking specifically at constructed wetlands and how they can be used at the farm scale. So here's an aerial view of the Franklin Farm. This is actually here in Lexington, Illinois. It is about a 250-acre farm, and you can see our wetland complexes here, which I'll go into in more detail in just a minute. So even though we focus quite a bit on the wetland research here, that's actually a great farm to do outreach. We've been able to do over 100 tours since 2005, and it's really an opportunity to showcase what people in the community, specifically farmers, can do on their property to help improve water quality. So there's also floodplain wetlands. There's a 15-acre restored prairie. We also have a remnant woodland that's going through different levels of restoration. And we've had several big open houses within the community to showcase what's happening on this property. So the big questions here are, how well does a wetland perform at reducing nitrogen and phosphorus for tile drainage? And then secondly, what size does it need to be effective? And the ground here is very, very productive. So to ask a farmer to take a lot of ground out of production is really going to be a non-starter. So if we're going to support the idea of a wetland, we want to make sure that they can be effective and not have to be a very big size. So what we have here, if you can see my cursor, we have our east, our gully, and our west wetland complexes. And they were all engineered to represent certain percentages of the drainage area. So how this works is that a tile will enter into the first wetland cell, and that will represent 3% of the drainage area. There's an adjacent pipe between cell 1 and 2, and when water transfers from cell 1 to cell 2, that now represents 6% of the drainage area. And this will happen again for cell 2 to cell 3, and as water transfers here, that now represents 9% of the drainage area. So the east, west, and the gully are all built to replicate that system. Now, ironically, we had to retile the farm so that we knew the drainage area coming into it. So that's what these red lines are here on your screen. And we have water quality instrumentation at the inlet and outlet at every single one of these wetland cells so that we can monitor not only the nutrients, but also the flow that's going in between the 3, 6, and 9% treatment wetlands. These wetlands are sampled weekly, and then the water samples were taken to the University of Illinois for analysis. So we've been doing this for a long time, over 10 years actually, and what we can say after looking at some of our data is that yes, these wetlands do a good job at reducing nitrogen and phosphorus. And what I'm showing here is values for nitrate nitrogen on the left, and then orthophosphorus or dissolved phosphorus on the right. We have our east wetlands in blue, our west in yellow, and then the gully is green. And that color scheme will continue throughout the rest of this talk. So let's first take a look at this top row here, looking at nitrate, nitrogen, and orthophosphorus. And what we can see here, and this is numbers on the y-axis here, these are low reductions, not considering seepage, basically what's in, what's out. And we can see that there's pretty high levels coming for both nitrate and phosphorus. But the numbers that we tend to report, and which is more accurate, is actually taking these low reductions, accounting for seepage. So we are going to have some loss to groundwater, and there's also going to be loss to evaporation. But even with that, what we see is that we do have total nitrate load reductions ranging from 13 to 48%, and we have dissolved reactive phosphorus ranging from 48 to 94% reduction. So it's definitely having some reductions here. And over time, we really focus more on the nitrate losses because Illinois does have a drinking water standard of 10 milligrams per liter. So focusing more on the nitrate issue has really been our message. And the good news is that we're actually seeing quite a bit of reductions happening in our 3 and 6% wetland size. So we don't need a big wetland to see a lot of reductions. Really, a lot of the activity is happening in the 3 to the 6%. So that's really what we were hoping for, and we've been able to convey that to the farming audiences. But what's been interesting is that we haven't delved into the phosphorus side as much, but whether we look at seepage or not seepage, we're seeing pretty high reductions in phosphorus even after over 10 years. And this is a little interesting because wetlands are known over time to actually accumulate phosphorus. You know, it just doesn't have a great place to go. And part of that is just due to the phosphorus cycle compared to the nitrogen cycle. So I do have to give thanks to Maria. I stole these slides from her. These are her slides, so all credit to her. But basically just to show here that when we look at nitrogen removal, specifically breaking down that nitrate molecule, some of it can be lost through nitrogen gas through the denitrification process, and that is a permanent loss of nitrogen. However, when we look at phosphorus, that isn't quite the case. It actually lacks an atmospheric phase. So phosphorus is either bound organically with plants and algae, which can be absorbed and then released, or it can be bound with inorganic, which would be particles such as clay or things like that. So it's got a bit more of a complicated cycle. So what's happening within our Franklin Farm wetland is a little bit of a mystery. But thankfully, to help answer that question, back in 2017, we were contacted by Jacob Berkowitz from the Corps of Engineers in Mississippi. And his team has been tasked with trying to work within the Great Lakes Valley and really even within the Mississippi watershed to determine what type of soils would be best fit for having types of wetlands that would really do the best job for retaining phosphorus within these regions. So they wanted to come specifically to ask the question of one, they wanted to measure phosphorus sorption capacity of the Franklin Farm wetlands, looking at the east gully and the west. And then secondly, they wanted to estimate that phosphorus removal and phosphorus dynamics to help aid resource managers such as ourselves in estimating the longevity and effectiveness of these treatment wetlands. So the soil sampling was pretty simple, basically just taking homogenized triplicate soil samples with this metal circular disc along the center of both the all of the 3, 6, and 9% wetlands. And then they took those samples back to their lab and did a whole bunch of analyses. But for the sake of this presentation, we're going to focus mostly on phosphorus and the malic extractable phosphorus, iron, and aluminum. And I really don't have any soils background, but I did get a crash course when Jacob was here, and he was basically showing us samples like this. And what we're really looking for clues as to where and how phosphorus might be bound, we're looking for little ribbons like this. This is basically rust iron oxide here. And that shows that there's probably at least some iron in these systems that are capable of trapping phosphorus. So that was an interesting find for me. All right, so we'll go through some of their data and we'll go step by step so we can kind of help explain this here. So what we're seeing here on the top is some of the numbers that they've come by extracting the phosphorus, the iron, and then the aluminum. And again, we've got our east in blue, we've got our west in yellow, and then the gully will be in green. And really just looking at this top row, what they found is that they were able to find phosphorus, iron, and aluminum throughout these series and without any real connection. So really there wasn't a clear trend here as to see if there was something that was truly binding the phosphorus. So there was a little bit of a hint that maybe iron and aluminum were affecting this slightly lower reduction in available phosphorus from the west, but really it's not very strong. So what they're saying is that this suggests that certain soil properties are what's controlling that phosphorus retention. And so that could be the amount of organic material, it could be tillage practices, it could have been even what happened before these wetlands were constructed. So there's really a lot more going on there that they can't quite place out. And then if we look here on the bottom graph, specifically on the bottom right here, we're looking at the soil phosphorus sorption capacity. And even though this is all on the same farm, all 3 wetland series exhibited slightly different capacities here. And what we're seeing is that the east is really, it looks like it doesn't have its capability to keep absorbing phosphorus, but really that's just showing that it's not going to be as strong. It's slightly losing. It can still absorb, but it's less than it used to be. Whereas the west still has a much higher capacity to do so, and the gully just seems to be more of a flow-through system. There's really just not much phosphorus being bound there. So, if we take a closer look here, now we're still looking at the extractable phosphorus, iron, and aluminum here, but this time we're breaking it down not only by east, west, and gully, but also by that 3, 6, and 9% wetland sizes here too. And what they found here is that when we take a look at iron and aluminum, there's no clear trend here. They're seeing various amounts of aluminum, whether we look at the smallest, if we're looking at the 3% or even up to the 9%. But they did see a significant decline with all sites with phosphorus. So what that's exhibiting is that those first cells are doing a pretty good job of trapping phosphorus, and there's less going to 6 and 9%. So there's probably more potential for reduction in those latter wetland cells there. And then lastly here, this is probably the big take-home message from their study. What I have here is water-soluble phosphorus on the top left in A, and then we have the phosphorus sorption capacity here in B. And what they found here is that water-soluble phosphorus decreases across treatment cells, but that's coupled with an increase in the sorption capacity. So these two graphs almost mirror each other. So basically, as we go from 3, 6, and 9%, there's less soluble phosphorus, but it has a better capacity to collect it. So what that tells us here at the Franklin Farm is that those first cells, that 3%, not only are they doing such a great job at reducing nutrients within the water, but they're also doing a great job of reducing those nutrients within the soils as well. It's also an indicator that perhaps we'll have to do management on the 3% cells before we'll have to do management on the 6 and 9%. And if we look at graph B here down at the bottom, we can also see that the east here in blue is likely going to stop reducing phosphorus a lot quicker than perhaps the west is, because just the capacity is going to be different there. The gully just seems to be, again, a flow-through system, not a whole lot happening right there. So this is really useful information for those of us as managers to figure out how to take the next steps to make sure that these wetlands still do a good job. All right, so some of our key findings from the study is that, first of all, looking at our water quality work, that a wetland representing just 3 to 6% of the drainage area can effectively reduce nutrient loadings from tile drainage. And then from the work from the Corps, what they found is that the magnitude of phosphorus retention really varied across wetlands, and not only comparing east, west, and gully, but also 3, 6, and 9%. And that really just underscores the influence of soil properties on those phosphorus sequestration dynamics. And then lastly, and this is the overall big picture, is that soil type, land use history, nutrient inputs, all these things are really important considerations for proper placement of wetlands within the landscape, because we want to be able to put these in places that we know that they'll be best fit and that they'll also be able to maximize their efficiencies for as long as possible. And this work was actually published in the Journal of Wetlands just this past year. And so we want to give congrats to our core partners for that. And I especially want to give a special shout out to Jason, the guy there standing with his arms up. That guy took hundreds of samples over the course of 3 days. So I really was impressed with that. And with that, I will take questions. Thank you.
Thank you very much, Krista. We have a couple minutes, Doug, for some questions, if we have any that have come in.
Yeah, so the first one, I think someone cut and pasted from an earlier presentation. It says, it seems like a great idea. Why isn't it happening?
Yeah, well, a few things. One, so wetlands are a tough sell in the agriculture arena. And part of that is because it's against the culture. You know, we spent decades, if not over a century, draining the landscape. So the thought of putting water back on is a little counterintuitive. And also wetlands, and specifically these kind of wetlands, are very expensive to construct. And even though we work very closely with the landowners and farmers to basically guide them through the conservation reserve process, it is a bit cumbersome, and the upfront costs are expensive, which we've really tried to help out with. And I would say also wetlands have almost solely a downstream benefit. The producer itself is getting the payments through CRP, but they're not exactly seeing that economic benefit on their farm. So all those things combined, I think, is what makes it a little bit slower.
Seems like a concept that's ripe for ecosystem service payments if we had
Exactly.
such. Okay, another question. How does this constructed wetland approach compare to prairie strip approach that's being used in Iowa to reduce nutrient runoff?
That's a good question. I'm not super familiar with that, but I do think there's any sort of, all these things kind of fit into this concept of edge of field practices. And so basically what that means is these practices that can be put at the end of a pipe or an end of an untiled area that could also just help with surface. So it really kind of depends if the practice is focusing surface water or if it's really impacting tile drainage water. So up in these areas for edge of field, we have things like filter strips and prairie buffers, pollinator habitats that really can do a great job at reducing surface water erosion and also help reduce nutrients. But if you really want to tackle the tile drainage issue, we're talking about things like saturated buffers or constructed wetlands like this.
And Matt Mangan mentions that in Iowa, they're routing tile lines into restored oxbow habitats, and they're seeing similar results.
Oh, that's great.
And then one more, maybe a quick question. Are there any groups pushing Congress to provide subsidies to farmers to construct and operate wetlands and plant cover crops?
Yeah, that's, I don't totally know the mechanism. I'm sure our GR team could really answer that a lot better than I could. But I do know that a lot of groups, like the Nature Conservancy specifically, always argues for a strong conservation title within the the farm bill. So it's certainly something that we know needs to be there. You know, we want for these practices that we know are a little more expensive and require taking land out of production, like they should be some benefits for that, whether that's big tax reductions or being able to maintain certain levels of value of the ground, things like that. So I know there's a lot of people out there trying to get that particular thing through Congress.